Well, thank you very much. Thank you, Yao, Paul, for the invitation. So let me start with some pictures. So this is in '93 in Rio, Stefan and Raghu. And this is in 2002 at Shannon, where Funaki gave me these pictures. So again, Vasu, Raghu, Stefano. All right, so I'll be talking about a reaction diffusion model. So let me define it. So I'll be working in finite d-dimensional torus. So there are nd points, and let me fix the notation. So configuration will be represented by eta. So eta x will be either 0 or 1. 0 if site x it's empty for the configuration eta 1 if it's occupied, and tau x will be representing the translation. So I will be here considering the superposition of two dynamics, one which is, I think, well known, the simple exclusion process, which is conservative, and the other one, it's non-conservative. It will be a Glauber dynamic. So the exclusion, well, in case you don't know, well, you just have these particles, and at rate 1, you exchange the occupation variables at two neighboring sites. So, well, if they are empty or occupied, nothing happens. If one of them is empty, the other occupied, you just exchange. You do that at each bond at rate 1 independently. And so this is conservative, so the total number of particles, it's conserved. And in consequence, you have a family of stationary states, which are very easy. They are just the product Bernoulli measure, so you fix a density rho, and at each site you place a particle with that probability. You leave it empty with probability 1 minus rho. You do that independently, and you get a measure which is reversible for these dynamics. And then together with that, we'll consider a non-conservative one, which is the Glauber dynamics. So here you fix certain function, which is a local. It will depend locally only on the configuration. And with that rate, you just flip the occupation variable at site x. So, well, if the site was occupied, you just remove the particle with that rate, and you can create also particles at empty sites. So this one, it's a non-conservative dynamics, as you can see. And maybe if you want to fix idea, let's consider this rate function, c. So let me call sigma s, which will take values now in minus 1, 1, 2 eta x minus 1. So you see that if eta x is occupied, this is 1. If it's empty, it's minus 1. And so the rate here, if site minus E1 and E1 are both occupied or empty, you see that this is 1. So you get a square here, gamma square. So gamma will be a parameter between 0 and 1. Here they have the same sign, so you get 2 times the sign. So if sigma 0 has the same sign, you get here a plus. With that, it's a minus, so it gets minus 1 minus 2 gamma plus gamma square. But if they have different sign, you just get plus 2 gamma. So it means that if the sign is the same, you jump, so you change the sign of that particle at a rate which is smaller than if they differ. And while if they have here different signs, you get a minus gamma square, and this is 0. So 1 minus gamma square if minus E1 and E1 have different signs. And why? Okay. So let me take this model in which we will speed up the exclusion part with n square, and the Glauber part with k. So k for the first part of this lecture will be fixed, but then it will be sent to infinity. Okay. So I'll keep this k. So let me call eta t this process, and we will be interested in the empirical measure. So let me call delta x over n direct measure at site x over n. Put a mass equal to 1 over nd if site x is occupied at time t. We have, therefore, a random measure, and we are interested in proving the hydrodynamical limit, so a law of large number first, for this empirical measure. So I will represent by P n P f the integral of f with respect to this random measure. Okay. So this model was introduced in '86 by De Masi, Ferrari, and Presutti, and Leibovitz, sorry. And what they proved is that, well, if you assume that your initial measure at time 0 converge to some measure which is absolutely continuous with certain density u0, then at later time t, you converge to the solution of this reaction diffusion equation. So you have the Laplacian here coming from the exclusion part, and a reaction term coming from the Glauber part. So what is this reaction term? The idea is that since you are here k is fixed, you are speeding up the exclusion part by n squared. So what you expect is that locally, so if you look in a box, the distribution of particles on that box should be very close to the distribution of the stationary state of the exclusion, which are Bernoulli measures. And therefore, what you expect is that the reaction term will be given by the expectation under the Bernoulli measure, which is the stationary state for the exclusion, of C times 1 minus 2 eta. What does that mean? Well, let me write this as 1 minus eta 0, which means that we are imposing that there is an empty site. So this is the rate at which you create particles, which I will call B of rho. So B of rho is the rate at which you are creating particles if the density is rho. And then you have a minus eta 0 C eta, which means that you have a particle, you are removing this particle, and this is the rate at which you are destroying particles. So beta minus D of rho, this is F. And if you take the model I proposed for C, what you get is that F can be written as minus the derivative of a double well potential. Okay, so you have a double well potential in which I will represent by rho minus and rho plus the stable densities, and here we will have 1/2, which will be the unstable density. Okay? So what's interesting of this model is that, well, this is an irreducible Markov process, so it has a unique stationary state. But if you go to the hydrodynamical limit, you see that this equation has many stationary states. So you can take, for instance, u equal constant equal to rho minus, rho plus, or 1/2, and you have a stationary state. And, but you have also stationary states which are not constant in time, they are just periodic functions. So a natural question is, well, to try to characterize the densities, the density profiles at which the stationary state concentrate. Right? So one thing we proved in dimension 1, so let me call S the stationary solutions of that equation. As I said, you have the constants, but also periodic solutions. And it has been proved that whatever initial density profile you start with, if you let time tend to infinity, the solution of that equation starting from this initial profile will converge to one of these stationary solutions. Okay. Well, using that result in the hydrodynamical limit, you can show that if you represent by mu n the stationary state of the Glauber plus Kawasaki dynamics, and you take a neighborhood of this of the set of stationary solutions, this set converge has probability close to 1 when n is very large. Okay. But of course, well, among these stationary solutions, you have unstable solutions. So I'll say that a solution is unstable if you can, you have seen already what a heteroclinic orbit is. So, but let me maybe remember, I would say that you have an heteroclinic orbit between two stationary states. If you have a solution of the hydrodynamic equation, which at t tends to plus infinity converge to gamma 1, as t tends to minus infinity converge to gamma 0. So I'll say that we have an heteroclinic orbit from gamma 0 to gamma 1. Okay? And you would like to refine this result by removing all stationary states for which there exists an heteroclinic orbit starting from this state. Okay? We're not able to do that. So what can we do? Well, what we did is to use the dynamical large deviations. So let me mention that you have a complete description for certain potentials V. So if V is a double well potential with satisfying certain conditions, you can characterize completely what are the set of stationary solutions of this equation. So what we did, following the ideas of Raghu, is to prove first a dynamical large deviation principle for this model, and then deducing from this dynamical large deviation a stationary large deviation for the empirical measure under the stationary state mu n. So let me introduce some notation. So let me define as I0t v. So this is the cost of observing the trajectory v in the time interval 0t for this dynamics. So this is the cost of a trajectory in this time interval 0t. And let us define, let's minimize the cost, starting from a stationary profile at time 0 and arriving at another stationary profile at time t, and let's minimize that over all time t. Okay, so this is the cost, essentially, that starting from rho, you reach a stable stationary state. So let me represent by ST the stable stationary states. Right? So what we could prove is that if you have an unstable, so those for which there exists this heteroclinic orbit, for any unstable stationary state, we can prove that this infimum is equal to 0. Right? You'll just follow, well, you know that there exists this heteroclinic orbit. You have to show that the cost of following this heteroclinic orbit is 0. Okay? By proving that, we could deduce that you can remove from your set all unstable stationary states. Okay? But this is not, well, okay, so this is what we can prove. The open question is if you take potential, double well potential, but let's say that which is not symmetric, so you have one of the wells which is lower than the other one, you would like clearly remove the stationary state which is, which has height higher than the other one, and well, this method doesn't allow you. So it's an open question to prove that you're able to remove these ones. So, okay, that we can't prove. So now let's continue what happens when k tends to infinity. So now we'll allow k to depend on n. Okay. So let me remind you that rho minus and rho plus are the stable densities. 1/2 is the unstable one. And we are considering the symmetric case. So, to present the main result, I will need to introduce what's called the standing wave solution of the equation. So we will be in dimension 1. What I claim is that there exists a solution now in R, which tends to, at plus infinity, it's equal to rho plus, minus infinity, rho minus, and to, well, there's an invariance by translation, so to fix uniqueness, let's say that at 0 it is equal to 1/2. So that will be the standing wave solution of our equation. Okay. This, well, can prove that this standing wave solution converges asymptotically, exponentially fast to rho plus, to rho minus, and that its derivative also decreases exponentially fast at plus infinity. Okay. So now the equation, so this is I removed k. So if I now add k, what you need to do in order to get the solution of this, it's just to shrink your equation to solution, which means that, okay, what I'm claiming is that if you define mk as m of square root of k times x, you get the solution mk, it's now the solution of this equation, which is the one which you're interested in, which means that telling you that to say that everything happens in a scale of size square root of k. Okay. So this equation will go from rho minus to rho plus in 1 over square root of k. So this is the important scale in this model. Okay. So now let's see what happens with this equation when I send k to plus infinity. So these have been considered by even Suner and Suganitz and Demoton and Schwarzman. In dimension 2 or higher, what they prove is that, well, if you start with an initial condition in which the set at which the solution, the initial condition, it's equal to, in our case, 1/2, that this is a smooth hypersurface. So if this is true, when you send k to infinity, uk will converge to a function which is either rho minus or rho plus. And the boundary between rho minus and rho plus is a smooth hypersurface in a finite interval, which evolves according to mean curvature. So this is how the solution of our equation evolves as k tends to plus infinity. In dimension 1, the situation is completely different. You'll need to rescale time by exponential of k in order to observe an evolution, because there you have a metastability phenomena which occurs. So Funaki, Tsunoda, and then later El-Qahtani, Funaki, Hilscher, Park, Turman, which is here, Funaki, Van Merse, Turman, and Tsunoda, proved the law of large numbers in the case in which you allow kn to tend to plus infinity, but at a very small rate. So you have to assume, and I'll try to explain that later, that kn is bounded by a constant time square root of log n. So by assuming that kn converges to plus infinity at a rate smaller than that, starting from an initial condition which converge again to a function which is either rho minus or rho plus, and whose boundary is smooth hypersurface, they proved that at later time t, so there exists a time, and for each t between 0 and this time, so this is the time the first singularity in this curve appears. So while the curve is smooth, you can prove that the solution of your reaction diffusion equation with now kn instead of k, so you're taking the reaction term multiplied by kn, converging to infinity at rate smaller than square root of n, that the empirical measure will converge to exactly, well, to this surface which is evolving according to mean curvature. So this is what has been proved. And so a natural question is to study what happens, what are the fluctuations of this curve, of this surface. And this is current work with Funaki and Sunder, which is here. So let me try to explain that. And to explain the results, let's remind what are the stationary solutions of this equation. So we are in a one-dimensional torus, and consider the stationary solution. So what you can prove is that, well, there exists a constant such that if the size of your torus is larger than this constant divided by square root of k, then you can find a solution of this equation in the interval minus L, L, which it's either positive with plus or strictly negative, larger than 1/2 or smaller than 1/2 in the whole interval, which at the boundary it's exactly equal to 1/2, and which is very close to rho plus or rho minus at the origin. So you have these solutions, which are either positive or negative. And as I said, since everything will happen in, and by piecing together these solutions, you can get solutions with as many layers as you want, provided that L is sufficiently large. So what we'll do, we'll take one of these solutions with 2 layers. And since everything is happening at in an interval of size square root of k, what we'll do is we'll expand that by k, square root of k. So we were thinking that actually we are working in the torus with size square root of k. So we are starting with this initial profile. And what we want is to study the fluctuations around the origin for that. So the idea is that we will start with an initial profile, which looks like that, but we'll expand it to square root of k. And we want to study the fluctuations of these dynamics around the origin. Okay. So let me represent by rho k this stationary solution, which has two layers. And we will start from that, and we want to study the fluctuations around that. Okay. So we are starting with a small perturbation of this stationary solution, and we want to investigate the evolution of this correction. Okay. So what you expect is that this correction will evolve according to the linearization of the hydrodynamic equation. So here I computed. So what you get is that this is the linearization of your equation. So this is the equation that should be describing the evolution of this fluctuation. Okay. So what appears here is this, this equation. So let me call AK this operator which appeared. So it's the Laplacian of W minus K V second of rho K, which is the stationary solution. So Carr and Pego studied this operator, and what they prove is that, okay, so let me call minus AK, so that you have these eigenvalues. The first one, it's equal to 0, and it corresponds to the derivative of rho K. So if you take the derivative of rho K, you see that it satisfies this equation. This equation will be equal to 0. Okay. But there is another eigenvalue, which is also very small, associated to essentially the absolute value of this derivative of rho K. So if you take, here is rho K. So what I claim is that the derivative of rho K, it's an eigenfunction of that operator, and this eigenfunction, it's associated to the eigenvalue 0. So the derivative of that will be looking like, well, you have something here and there, and the absolute value, I claim, it's close. Well, it's an approximation of the eigenfunction associated to the second eigenvalue. But what they prove, and this is more important, is that there exists a constant, and that uniformly in K, all these eigenvalues are bounded below by K times a strictly positive constant. Okay? So they are very large. So you have two very small eigenvalues, and all the other ones are very large, which means that if you take the semigroup associated to this operator, it will project on these first two eigenfunctions, and the other ones will go to 0. So let me call E the derivative of the standing wave, normalized. And what follows from this result by Carr and Pego is you take now a function f, which is defined in R. You shrink it to have a function between minus 1/2 and 1/2, so we defined on the torus. You apply the semigroup, then you expand it again, and what I claim is that this function, it's converging, it's projected in f times E. Okay. So what is the result? As I said, you take your solution with two layers, the stationary solution with two layers. You consider a product measure so you are in dimension D now, so you take in one dimension this layer, and the other one you take translations invariant. So essentially you have a wave which is translation invariant in the other directions. Now you take a product measure which follows this density profile, and you study the fluctuations around this density profile. So you introduce your density field. As I said, you need to expand your function, so you need to consider your test function on this scale, square root of k. Okay. Since you want to study your test function in this scale, you have to redefine your density field by, usually you divide it by square root of nd. Now you will be dividing it by square root of nd times square root of k. You need to do that in order to keep the noise of size 1. Once you do that, you realize that at time 0, this density field, since you're starting with a product measure, will vanish. You let your process evolve, and what you'd like to prove is a limit for your density field at time t. And okay, so for later use, let me just introduce the Dynkin martingale. So if you take a test function, mf will represent the Dynkin martingale associated to f. So what are the results? First, we are able only to consider dimension 1 and 2, and I'll try to explain that in a second. K again should increase at most as square root of log n. So we're not able to go further than square root of log n. And what we can show is that this density field is converging to a field yt, which is, well, in dimension 1. So in dimension 1, you have your standing wave, and you have a fluctuation around this standing wave. And how is the fluctuation? Well, it's given by the derivative of the standing wave times the Brownian motion. Okay, so you start at 0, and then, but mind that at x, this is absolutely rigid. Okay? So there is no fluctuation in the x direction. You're just fluctuating in time. And this is reflects actually the fact that you have this metastability phenomenon, so that this system is extremely rigid in the x direction. In 2 dimension, what you prove is that your field converge to Ex times Zty. So in the second direction, let me represent by Zt the solution of the stochastic heat equation. And the field can be represented as Ex times the solution of this stochastic heat equation in the other direction. And this is what you get at dimension 2. So these are the results. So let me try to explain why, what are the difficulties. So what you do is you write down your martingale. So you represent your field as a drift term plus a martingale. The martingale will converge to the noise. And this will be not very difficult to prove that this martingale converges to the noise. So what you need to consider is the drift term. And what you'd like to do is to represent this drift term as y applied to an operator A on f. If you do that, well, you're essentially proving that your equation yt is converging to the solution of this linear stochastic differential equation. Okay? So let's try to do that. So you start computing your drift term. So you have a piece which corresponds to the exclusion part and a piece which corresponds to the Glauber dynamics. So here you observe that you have the discrete Laplacian. The discrete Laplacian in the second coordinate will just give you a factor 1. But in the first coordinate, since you're expanding your test function by square root of k, you will get an extra k. So you get an extra k for the derivative in the first dimension, 1 for the other terms. So this 1 will be a term of smaller order. And then you get k because you're splitting your Glauber dynamics by k. And here, the problem is that you have this local function, and you would like to replace this local function by a function of the conserved quantity, which is the density of particles. So the main problem will be to replace this local function h by a function of this density field. And this is called the Boltzmann-Gibbs principle, which tells you that indeed you can replace h minus its expectation by a constant, which will be, you have to understand that as a Taylor expansion of this local function as the derivative of this function times eta x minus 1. And this is the main, the main step the main technical step in this proof, and all the problem comes from the fact that you have this extra factor k. So you have a blowing up term here that you need to control. And to prove this Boltzmann-Gibbs principle, we use these ideas by Jara and Menezes about these entropy estimates. So here we are in non-equilibrium. In non-equilibrium, the tool we have in order to estimate terms are given by these entropy inequality. And once you do that, well, once you can replace, you get your drift term, as I said, given by some differential operator applied to f. In our case, this is just k times, I'm representing here by hat hk. Well, you take your function f, which is a function, a test function defined on R. It has compact support, so you can think that it's defined in the torus minus square root of k square root of k. So you are allowed to apply the operator ak to it, multiplied by k, and then you just consider that and you expand it again. And you use then the result following by Carr and Pego that you are projected on E to get the result and out. So the main step, it's really the Boltzmann-Gibbs principle. Once you have that, the rest of the proof, it's quite straightforward. And as I said, well, here the problem, it's, and why I want to present that, because, well, I would like very much to extend this proof to larger scales. So I expect that you can help us that, to extend this proof, which is an estimate of the entropy, for which allows to consider larger scale. Okay, so let me remind you that you define the entropy as the supremum of this difference. Okay. So I don't have much time, so let me skip this part. Okay, so you define the entropy. Now you want to consider, you have a reference measure nu, you have your state space, so you started from u, you let the process evolve, you have a new state at time t, mu st, and you want to show how the entropy evolves. So if you're, since the measure you're considering, it's not a stationary state, this entropy is not decreasing, but you can show that its derivative, it's bounded by L star applied to 1 of ft d nu, where f it's just the Radon-Nikodym derivative. So you're integrating here with respect to the state of the process at time t. And here it's minus the Carré du Champ, which is a positive term. So if you want to estimate the entropy, you want to prove a Groenewald type inequality. So you have to estimate this expression. Well, you have here a positive term, so a negative term. So you are allowed to estimate this expression by what I will call the energy and the entropy. So this is the theorem we could prove. So by using this Jara-Menezes technique, we were able to prove that the derivative of the entropy is bounded by k squared times the entropy plus this small error term. And of course, since you have k squared here, by using the Groenewald, what you get is that the entropy is bounded by exponential k squared. And this explains why you can take k only as the size of square root of log n. Okay? And, okay, so this is true for in any dimension. But if you want to prove the Boltzmann-Gibbs with these bounds, you can do it only in 2 dimensions. This is why we are stuck to 2 dimensions. Because, well, this bound on the entropy, it's not good enough. So here, okay, you're free to choose what is the reference measure you want. So here we just took the reference measure as the product measure associated to the stationary profile. Okay. Why we did that? Well, we said we are speeding up the exclusion by n squared, so we expect the state to be close to a Bernoulli measure. But of course, you're perturbing that by a Glauber, and you're speeding up the Glauber by kn. So maybe if instead of using nu as a product measure, you use something which has 2 or 3 points correlations, you can get a state which is closer to the actual stationary state and get better estimates. But so you have to have an idea how to define this stationary state in order to get better estimates here at the entropy. So you'll have other terms that might cancel. Okay, if you know what the degree of a function is, you just express everything in terms of the degree. You add terms that will provide you higher orders degree that can kill the previous, and you might improve this estimate. So this was done by Bodino and Dagalier for the exclusion in contact with reservoirs, but there, the stationary state, it's really close to Bernoulli measures. So here we are not so close, so okay. So we need new ideas. So this is, I think, well, one problem which I expect novelties in the next few years, and this is why I'm mentioning here. And also, if you are able to take case of larger order, you might be able to prove a Boltzmann-Gibbs principle of higher order, and that will give you nonlinear equations. So here, typically, if you could get n to the order of 2/7 in dimension 1 or 4/7 in dimension 2, you would get nonlinear equations for your density field. So the density field will be evolving according to nonlinear SPDEs, and it will be very nice to derive nonlinear SPDEs from interacting particle systems. And so everything boils down to this estimate in which, well, I think the problem here is to get a better insight on these stationary states. Okay. And with that, I stop here. Thank you very much for your attention.